We're now going to work an example problem looking at the Newton's or conservation of momentum for the case of rectilinear acceleration of the control volume. And what we'll look at is that problem of a rocket. Okay, so there is our problem, and what I've drawn is I've drawn a control volume around our rocket, and you can see it sketched here. I've drawn the control volume to be right across the nozzle exit, and we can see that we have our inertial reference frame that is fixed and not moving, and then we have our moving reference frame that in this particular case it turns out that being that it's on the rocket, it's actually accelerating, and consequently we have the rectilinear acceleration problem. So what we are told to find, other things we are told is that the rocket starts from rest, so it starts from being stationary, not moving. We're told to neglect the drag forces across or on the rocket being exerted by the air resistance. Fuel consumption we're given 5 kilograms per second, and that's equal to the mass flow rate leaving. Exhaust velocity 3,500 meters per second, and then finally the original mass of the rocket is 400 kilograms. So we're asked to find a couple of things. So we're asked to find the initial acceleration a naught, and then the velocity as a function of time. So what we have here, this is an example problem involving rectilinear acceleration. So we know in terms of a solution that the equations that we can apply, one would be the y component of linear momentum for the case of linear acceleration. So let's look at that. And if you recall in last lecture segment, what we did, we came up with an expression that was basically a modification of the form of the momentum equation, where what we did is we modified it with this term that I'm writing right now, pertaining to the acceleration of the reference frame. And then everything else was the same. However, we had to be careful of measuring the velocities with respect to the moving reference frame. And then finally we have the mass flux leaving term. The last three terms give us that. And then we have conservation of momentum, or of mass, the continuity equation. Okay, so what we're going to do, we're going to begin by looking at conservation of mass, and we'll work with that first, come up with an expression for the mass of the control volume, and then we'll go back to the y momentum equation. So this first term here can be expressed as being the mass of the control volume with respect to time. And that is equal to the integral over the control surface. I'm just using the continuity equation here, and I basically moved one term to the left and kept the other on the right. So with this, if we're looking at the bottom of our rocket, we have to be careful here with the dot product. But essentially we have a control surface like this. The vector leaving is in this direction, the area vector is in that direction, and consequently this turns out to be a positive when we do the dot product. So what we end up with and that is equal to minus m exiting, and I'll put a dot over that. So that's the mass flow rate exiting our control volume. And with this, what we come up with is an integral equation so we want to integrate that. And the control volume mass is only changing with respect to time, so that would be an ordinary differential equation, and what we then get is mcv is minus the mass flow rate leaving times time plus some constant of integration. We apply a boundary condition, and we were told that the mass of the rocket, or the mass of the control volume at time 0, was equal to m0, and I think we were given 400 kilograms. So with that, we can get C is equal to the original mass, and from that, we get the mass of the control volume is equal to the mass exiting multiplied by time, the mass flow rate exiting times time, plus the original mass. So that's kind of an obvious, intuitive expression. Basically just saying the mass leaving, you subtract that from the original mass, and that gives you the mass of the control volume as a function of time. So we get that expression from continuity. Now what we want to do is go on to momentum and take a look at the y component of momentum. And for this, the body force is just going to be the mass of the control volume times the gravitational vector, and it's minus because it's acting down. The term that modifies and enables us to apply control volume analysis for the accelerating reference frame. And then on the right-hand side, okay. Now, what we're going to do, we're going to make a simplification here, and this is a bit of an approximation, but I'm going to get rid of the time rate of change term, and I'm going to use two different reasons for justifying that. One is that the unburnt fuel and the structure of the rocket is not moving with respect to the accelerating control volume. And the other one is that the nozzle exhaust velocity is steady. So even though the mass is very large, we have a steady velocity more or less and a large mass that really is not changing that much with time. And consequently with that, we can then make the approximation that the time rate of change of that term is small. So what that leaves us with then is this term here that we're going to take a look at and work a little bit more with. So let's look at that now. So here, the only mass leaving the control volume, or the only place crossing a control surface, is the exhaust itself. And so we have the exit velocity is VE. And if you look at the vector, VE is in the down direction. So I would write minus VEJ. And that's why we have a minus for the first velocity term. And then that's multiplied by the mass flux, the area vector is in that direction, so the dot product comes out to be a positive, so we express that as being a positive here. And so rho VE area exit, that is nothing more than just the mass flow rate exiting. So m dot E, which we expressed earlier from continuity. So what we can do, we can take this and plug it back up into our equation for the y momentum equation. We have the gravity term, or the body force, the acceleration of our reference frame times the mass of the control volume, and then on the right hand side, VE times m dot E. So what I'm going to do, I'm going to isolate the reference frame acceleration. And I'm going to rearrange this. And also what I will do is I'm going to go back to the result that we got from the continuity equation right here and plug that in as well. And so we get this equation here for the acceleration. And we were asked to find the initial acceleration. So for part A, we have at time t equals 0. So what you find, plugging in the values, is right at the beginning of the liftoff of the rocket, the acceleration is 3.46 Gs. And the second part we were asked to find was the velocity as a function of time. And so for that, we will integrate the acceleration expression. And upon integrating this, we end up with the following relationship or expression. So that gives us an expression for the velocity as a function of time. And plugging in the values that we were given for the problem. So that becomes an expression. We can do calculations at different times. So let's say velocity at 10 seconds. We would get 369.3 meters per second. So, assuming that the speed of sound is around, it would be the square root of gamma RT, approximately 340 meters per second. Within 10 seconds, we would have exceeded the speed of sound, and so at that point, the rocket would be going supersonic. And then it would continue to accelerate. If you plot out the velocity profile for this problem, I don't have it plotted neatly, however, it would look something kind of like this. Given the relationship that we've drawn, we would have t on the horizontal, u of t this way. You would get a function that would kind of do something like this, and then it would start going up and climbing very, very quickly. So you can see it takes a while for the rocket to get going in terms of velocity, but then when you get later on in time, by time 80 seconds, which I think is right in around here somewhere, by then, given the mass flow rate we have, I think you've depleted all of the mass of the rocket. And that's why the velocity is going very, very high there, because you don't have a lot of mass that you have to accelerate. So anyways, that's the case, solving a problem with an accelerating control volume. The biggest thing to remember is the fact that you have to deal with a modified version of the momentum equation. Where was it? I think it was right here. And the modification was due to this term here for the accelerating reference frame. So that concludes this problem and this lecture.